and welcome to the study of electromagnetic induction. In this chapter, we'll basically look at how a changing magnetic field produces an induced EMF. We'll study Faraday's law of electromagnetic induction, Lenz's law. We'll study the functioning of alternating current generators, motors. We'll also look at the new component in this chapter called inductor, or the phenomenon of inductance, and how it can be combined with a resistance and a capacitance to produce what's called an LRC circuit. Let's dive into these concepts. So we know that whenever a current flows through a conductor, a magnetic field is produced around it. So a current always produces a magnetic field. Now in this chapter, we're going to see that a changing magnetic field produces a current. A changing magnetic field producing a current is called electromagnetic induction. Remember that if the magnetic field, however strong it may be, does not change, then the induced EMF or induced current is zero. So the key point is that the magnetic field has to change in order to induce an EMF or a current. So that's a very important point to notice. Okay? And then we also come and see, we'll talk about generators, transformers, microphones, a particular type of microphone called the condenser microphone, the airport security scanning systems, and finally the damping mechanisms. So here is a circuit or an arrangement to demonstrate electromagnetic induction. So this experiment was actually done by Faraday, and it consists of an iron core here, and on top of the iron core there is a coil, and this coil is connected to a battery through a switch. But at the bottom of the coil, at the bottom of the iron core, there is another coil that's connected to a galvanometer. So when the switch is closed, current begins to flow through this coil, the top coil, but that current increases from zero to a maximum, which means that it produces an increasing magnetic field, because the strength of the magnetic field depends on the strength of the current. So as the current increases from zero to a maximum, the magnetic field also changes, increases. This changing magnetic field is linked with the bottom coil because it's nearby. And so the coil at the bottom experiences a changing magnetic field, which produces a current in it. And that's when you see the galvanometer show a deflection to one side. Now, if that is what happens when the switch is closed, you know what's going to happen when the switch is open? When the switch is open, the current in the top coil decays, which means its value drops from a maximum to a minimum or to zero. That again changes the magnetic field. This time it decreases the magnetic field. And this changing magnetic field associated with the bottom coil once again induces a current in it, but this time the current is going to flow in the opposite direction. So we see the galvanometer move in the opposite direction. So in summary, a changing magnetic field induces a current, and the direction of the induced current depends on the changing magnetic field. We're going to look at this in detail in the sections to come. But there's another experiment that Faraday did where he had a magnet move towards a coil connected to a galvanometer. So this is Faraday's experiment number 1. We're going to look at Faraday's experiment number 2. Here it is. So in this case, we have the north pole of a magnet moved towards a coil connected to a galvanometer, and immediately the galvanometer shows a deflection in one direction. As you can see, the pointer moves to the right. But when the same magnet is taken away, again, there is an induced current, but this time the deflection of the galvanometer is in the opposite direction, which means the induced current is opposite. Likewise, you can see when the poles of the magnet are reversed, like this one, you have the south pole coming up. You see that the deflection is one direction, south pole going down, deflection is in the opposite direction. So, of course, the direction of the induced current clearly depends on what pole of the magnet is moving and is it moving towards or away. But what is interesting is to notice that in the last setup, you have a magnet that is kept stationary inside the coil. So the coil experiences a magnetic field, but if the magnet is not moved, the magnetic field of the coil is not changing. Now, changing is the most important word. If it's not changing, the galvanometer shows no deflection. Principle of the generator. To understand this principle, let's consider that there is a surface kept like that, and as you can see, there is a magnetic field acting at an angle to the surface, but the angle is taken with the perpendicular drawn to the surface. Did you notice that? So that's the magnetic field, and the angle is taken with the perpendicular, not with the surface. It's taken with the perpendicular. So if the magnetic field was along the perpendicular, then the angle is 0 degrees. But if the magnetic field was this way and the surface was kept this way, so now you see the magnetic field is straight down, the surface is kept this way, which means the perpendicular to the surface is that way. The angle between the perpendicular and the magnetic field is now 90 degrees. And you can see that when it's this way, all of the magnetic field passes through the surface, but when it's this way, nothing goes through the surface. Therefore, the magnetic field passing through a surface is given by B cosine theta, where B is the strength of the magnetic field and theta is the angle between what? Between the perpendicular to the surface and the magnetic field. Cosine 0 is 1. That's why when the surface is this way, the magnetic field is this way, the angle being 0, maximum field goes through it because cosine 0 is 1. And when cosine 9 is 90, that is 0, no magnetic field passes through the surface. So that's very important to notice that the magnetic flux, the symbol for magnetic flux is phi. Sometimes we put phi sub B to show that it's a magnetic field, and it's always given by BA cosine theta. B is the strength of the magnetic field, A is the area of the surface, and theta is the angle between the perpendicular drawn to the surface and the magnetic field. The units of magnetic flux are Tesla meter squared, because B is in Tesla, A is in meter squared, and cosine theta is just a number. Now that is the principle of the generator. So basically in a generator, we will have a coil like that continuously rotating in a magnetic field. As the coil continuously rotates in a magnetic field, the magnetic flux associated with it goes from a maximum to a minimum to a maximum to a minimum. So since the magnetic field associated with it is continuously changing, there is a continuous induced current produced. It's that simple. This is the principle of the alternating current generator. So here it is, the principle of a generator. A coil rotated in a magnetic field causes the flux to change continuously, producing an alternating EMF. Right? So now let's look at Faraday's law. According to Faraday's law, let me speed this up, the induced EMF is proportional to the rate of change of magnetic flux. The induced EMF is bigger when the rate at which the magnetic flux is changing is also bigger. So if you change the magnetic flux faster, you get a bigger induced EMF. And it also depends on the number of turns in the coil. N is the number of turns in the coil. Delta phi by delta T is the rate of change of magnetic flux. Delta phi is the change in magnetic flux. Delta T is the change in time. The ratio is simply the rate of change of magnetic flux. So here is a simple question. A coil has 100 turns and the flux changes from 0.5 Tesla meter squared to negative 0.5 Tesla meter squared in 5 seconds. What is the induced EMF? Right there. Now be careful. The change in the magnetic flux is actually 10 or negative 10. Whatever way you take it, it is not 0 because it went from 5 to negative 5. So the difference is double. So that's what is shown here. That's the change, final takeaway initial, and then the time is 5 seconds, and then there is 100 turns. So you get the induced voltage or the induced EMF as 20 volt. Now, while Faraday's law gives the magnitude of the induced EMF, Lenz's law gives the direction of the induced EMF. And this can be a little confusing. Therefore, please pay close attention. All right, so in this diagram, you have a magnet that is thrust into a coil. So that's the coil. The magnet is quickly moved into the coil. And you can see that the magnetic field of the bar magnet is from north to south. So here is the field of the magnet. Now, according to Lenz's law, since the coil experiences a change in magnetic field, an induced EMF is going to be produced in it. Well, sorry, that's by Faraday's law. But the direction of that induced current is going to be such as to oppose the change in the magnetic flux. Now that's tough. So let me break that down. So when you move the magnet towards the coil, what is happening to the magnetic field associated with the coil? Is it increasing or decreasing? Remember, the magnet is coming closer, so the magnetic field associated with the coil is increasing. And according to Lenz's law, the induced current should oppose the increase in magnetic field. That means it should set up a magnetic field opposite to the increasing magnetic field because it has to oppose it. And then we can use the right-hand rule that we have studied, as you can see here, with the thumb pointing in the direction of the current and the closed fingers towards the tip giving the magnetic field. Now when you use that, you can clearly see that looking from the side of the magnet, the current has to flow counterclockwise. Why? In order to produce a magnetic field B that is opposing the magnetic field of the magnet. I hope that's clear. But here is a second and third situation that's coming up, and we got to find the direction by the application of Lenz's law. So once again, the direction of the induced EMF is given by Lenz's law. And according to Lenz's law, the direction of the induced EMF is always such as to oppose the changing magnetic field. Let me read that. The induced current creates a magnetic field that opposes the change in flux. So that's Lenz's law. Here is the second situation. Now you can see that the same magnet is moved away from the coil. Away from the coil. That means the magnetic flux associated with this coil is decreasing because it's going away. Therefore, the induced current should be in such a direction as to produce a magnetic field in the same direction. In the same direction. You can see that. So the magnetic field due to the magnet was in this direction, right? In this direction. And the induced current also produces a magnetic field in the same direction. Why? Because the magnetic field is decreasing and wants to oppose it. Which means that now looking from the side of the magnet, the current has to be flowing clockwise. I hope that's clear, and you can make that out, but you can test it yourself using the third diagram here, in which case the poles are flipped. It's now the south pole of the magnet facing the coil, and it's coming in, so which means now the current should again be clockwise. I hope that makes sense. Here is an application of electromagnetic induction that is used in recording audio and video onto magnetic tapes. So basically, a magnetic tape has iron oxide deposited on it, which is a ferromagnetic material. And the playhead or the recording head receives changing currents from a microphone. And so the magnetic field fluctuates. And when the tape passes touching the playback or recording head, that changing magnetic field redistributes the iron oxide in a certain pattern. And so from that pattern, we are able to get back the audio or the video that was used for recording. So next up is motional EMF. So before getting into the concept, think about an airplane flying, let's say horizontally. And you know the earth has a magnetic field. And so when that airplane is flying horizontally, it is actually cutting the vertical component of the earth's magnetic field. Rather, it's going across the vertical component of the earth's magnetic field. So since it's moving fast, there is a huge change in magnetic field associated with it, and therefore there will be an induced current produced across the tip of the wings. So now to understand that, we have to look at a conductor as shown here moving through a magnetic field. Now this is just an arrangement of a circuit with a resistance where this part is a rod that can be moved over these two parallel rods. And whenever you see a pattern shown this way with X's, remember that is the back of an arrow, which means that the magnetic field is perpendicular to the plane of the screen and into it. On the other hand, if you see the dots, then you're seeing the tip of the arrow, which means the magnetic field is again perpendicular to the screen, but it's coming out of the screen. So in this case, the magnetic field is perpendicular to the screen, but into the screen. And let's imagine that this conductor is moved outwards, as you can see. As it's moved outwards, it's going through a certain area. All right, so it's sweeping out a certain area, the shaded area. And therefore, you see that it's experiencing a changing magnetic field because the area here keeps changing. And the induced EMF is actually given by the product of the magnetic field, strength of the magnetic field, which is B, the length of the conductor, and the velocity with which it's moved. And this is the formula when the conductor is moving perpendicular to the magnetic field. Okay, just the product of these three when it's perpendicular. So let's work out a simple question. You have a 1 meter rod moving perpendicular to the Earth's field, and we have to find the induced EMF. Here is the strength of the Earth's field, and the length of the conductor is 1 meter, and if it's moved at 3 meters per second, you get a very small induced EMF of 150 microvolt. Now, since there is a motional EMF, we see that a current can be caused in a loop in a conductor moving through a magnetic field. All right, so what you see here is actually a pendulum made of aluminum. It's just an aluminum, flat piece of aluminum that is allowed to swing between the poles of a magnet. So you have the north and the south pole, and this piece of aluminum is swinging between. But as it swings, it experiences a change in the magnetic flux, and so an induced current is actually set up in the entire body of the aluminum plate in closed circuit. So all across or all through the aluminum plate, you have small currents in the form of eddies. That's why it's called eddy current. And this eddy current opposes the change in magnetic flux, which means indirectly it opposes the swing of the pendulum. So when you try to swing it, you will see that it'll just go through it and stop. But on the other hand, if you have the same aluminum plate with slots in it, then we see that the damping is smaller. It will make a few more swings. Why? Because now you have a reduced space because of the slots and smaller eddy currents. Now if you take an insulator, like a piece of wood, thin piece of wood, and make a pendulum, and when it swings, you see that there is no damping because wood is an insulator and no currents can flow through it. So this is the idea of eddy currents, and it's also used for damping in instruments. Whenever you do not want the pointer in an instrument to keep oscillating, because we need to read the current or the voltage, we use electromagnetic damping. Electromagnetic damping can also be used in braking systems to a great effect. And so electromagnetic damping has many applications. So here you see eddy currents are currents caused by relative motion of a conductor and a magnetic field. Right? That's number one. Eddy currents produce magnetic damping is number two. And whatever I've explained is now very clear in these diagrams. With slots, and especially if this bottom part is cut out, there will be minimum damping. But when you have a plate, there will be maximum damping. Here are three quick applications of electromagnetic induction or eddy currents. First of all, magnetic damping in balances. Here you have a rotating disc, a simple rotating disc that produces magnetic damping, and therefore the balance stops oscillating quickly. Otherwise, it would have taken a long time for it to become stable. In the second application, you see metal being dumped from a truck, and you have a magnet here, And any kind of metal, when it moves past that magnet, you're going to have eddy currents in it, and these eddy currents oppose its motion. So whatever metal it is, aluminum or iron, it need not be ferromagnetic. Any metal is going to get bunched up there and it'll stop, while other materials, which are non-metals, will simply fall through. Similarly, you have in a metal detector, you have eddy currents in a metal change the current in a secondary coil in this mine detector. So any metal in the ground is going to change the current in a secondary coil, and so we can detect any metal in the ground. Now, we already looked at the principle of the electric generator, where you simply have a coil rotating in a magnetic field. Now, to allow for rotation, you have carbon brushes that are brushing against what are called slip rings. So you have brass rings where you have the copper brushing against it so that there is provision for it to turn without messing up the cables. And as the magnetic field changes when the coil rotates, there is going to be a continuous induced EMF. So a continuous rotation of the coil produces a continuous alternating EMF, and the strength of that EMF, or the magnitude, depends on the number of turns in the coil, the area of the coil, the strength of the magnetic field, and the speed of rotation. So 4 quantities. I'm going to write them now. E, which is the induced EMF, is NBA. That's easy to remember. NBA omega sine omega t. N is the number of turns, A is the area of the coil, B is the strength of the field, and omega is the angular speed of rotation. So that is the formula for induced EMF in a generator. In fact, these 3, N, B, and A, omega, all are constants. So these 4 together is called the peak value of the EMF, the peak value of the EMF. All right, so look at the nature of the current or the EMF produced. That's why it's called alternating, because in one half cycle it's positive, in the next half cycle it's negative, and again it goes positive. So that means it first flows through the coil in one direction, then it flows through the coil in the opposite direction, the currents. That's why it's called alternating EMF. And also these 4, as I explained, are constants, and it's called the peak value of the EMF, which is E naught here. So you see that this is the peak value of the EMF. So whenever we talk about alternating EMFs or currents, it's going to have a peak value. Now, in the case of the DC generator, there is a small change. And the change is that you can see here that instead of using 2 slip rings and 2 brushes, we use 1 split ring. So it's 1 ring split into 2 halves, and then the brushes are touching against the opposite parts. So as the coil rotates, this is going to move, the brushes are going to move, and then you will see that when the current in the coil reverses direction, because of the split rings in the external load, the current is also going to change direction. So 2 negatives make a positive, and therefore we see that you get current flowing only in one direction. It's not perfect DC, it's called pulsating DC, because it's not a constant magnitude, it's a pulsating DC. But what's important is the current flows in one direction only. This is the concept of back EMF. Let's take it slowly. The word back EMF itself means there is an EMF induced which is opposite to the applied EMF. So as shown in this diagram, we can see that there is maybe a motor, that is switched on. But as the motor increases its speed of rotation, there is an induced EMF produced, and that induced EMF is going to become bigger and bigger. Why? Because the induced EMF depends on the rate at which the magnetic field is changing. So that's called the back EMF. The induced EMF is called the back EMF. So you have the driving EMF, which is the applied one. You also have the back EMF. Is the back EMF constant? No, it's not. When the motor is switched on, what's the value of the back EMF? 0. All right, so that means the current at the start of a motor is going to be really high because you do not have the negative quantity. So when you switch on a motor, there is a great chance of burnout in the coil of a motor because of this high current. That's why we always need to have a starter resistance in a motor. So when it just switches on, the starter resistance is going to decrease the current in the coil. But as it picks up full speed, we don't need the resistance anymore, because by that time the back EMF has increased to a bigger number, and so the current will be small. That brings us to a very important application of electromagnetic induction, namely a transformer. Now, we know that currents or EMFs are produced by generators, and then these have to be brought over long cables to factories and homes. Now, while we're bringing that current through the cables, there's going to be a lot of heat produced, and so a lot of wastage. The heat produced depends on the square of the current. So in order to produce a smaller amount of heat and less wastage, the current has to be really small. So the current in long distance transmission cables has to be really small. How do we do that? We do that by using a step-up transformer. I know you're going to get confused. The step-up part means the voltage increases, but the current decreases. So a step-up transformer is used at the generating end, and then the current at a very high voltage but low current comes over those cables. But when it comes to our homes, just before that, we use a step-down transformer. What does a step-down transformer do? It decreases the voltage and increases the current back to usable levels. So that's where transformers play an important part. So the important equation in a transformer is that the ratio of the secondary voltage to the primary voltage is equal to the ratio of the number of turns in the secondary to the number of turns in the primary. All right, I've not even described what a transformer is, but you can see it's basically an iron core. It's iron here. One side you have a primary coil, the other side you have a secondary coil. And there is a voltage in the primary, voltage that you give to the primary, and because it's alternating, it's going to induce a voltage in the secondary. There's also going to be a current in the primary, a current in the secondary. So now this should make sense. Vs by Vp is equal to Ns by Np. That's for voltages. But for currents, if it's an ideal transformer, which means there is no wastage of power, and you know power is the product of current and voltage. In that case, the power in the primary is equal to the power in the secondary. So Ip times Vp is equal to Is times Vs. And that means if Ns is greater than Np, voltage in the secondary is going to be greater than in the primary. That's a step-up transformer. All right, which again means the current in the secondary is going to be less than the current in the primary. So that's why I said at the generating end, you use a step-up transformer. Why? In order to have a smaller current on the secondary, which is going to flow through those cables. Right? Well, finally, we have come to where I can introduce the inductor. Remember, in the previous chapters, we studied about a capacitor that stores energy as an electric field, a resistor that simply dissipates or wastes energy, and now we have an inductor which can store energy as a magnetic field. So a capacitor stores energy as an electric field, while an inductor stores energy as a magnetic field. Very important. What is an inductor? Simply, we know that if you have two coils near each other, and if you apply an alternating current to one of them, because the current is fluctuating, the magnetic field is going to be continuously changing. And so there will be an EMF induced in the second coil, which can be readily seen from a galvanometer, which will go crazy. It will keep going left and right. So I've written alternating currents create changing magnetic fields that induce EMF in a neighboring coil. This is the idea of an inductor. So a coil is an inductor. And you can increase the inductance of a coil by having a larger number of turns, and also by using an iron core. That means push a bundle of iron wires through the inside of the coil. You are going to get a large inductor. So here there are applications of inductance again. In a clothes dryer, electric clothes dryer, we do not want any inductance effects, because when you send AC through a coil, it's going to induce electric currents in the body of the electric dryer, which is a metal, of course, and anybody touching that would get an electric shock. In order to avoid that, you know what is done? The coil is wound in two halves. The first half, the coil is wound in one direction, and then in the second half, it's wound over it in the opposite direction. What's the advantage of this? The advantage is that the magnetic fields through these two coils cancel out. Therefore, there is no net change in the magnetic field, or the induced current is zero. Well, the security gate at an airport, as you can see, is actually a metal detector, and it is a transmitter and a receiver. So on one side you have the transmitter, of that gate. One side you have a transmitter that transmits an AC signal, and on the other side you have a receiver that picks up that AC signal. So when a person passes by and has some metal on him or her, that metal is going to change the magnetic field, and so the signal received by the receiver is going to suddenly change because of the metal moving between the transmitter and the receiver. And that's how metals can be detected. But remember that plastic or any non-metal cannot be detected using this capacitance circuit, where you had the resistance and the capacitance connected in series. Now we have a resistance and an inductance connected in series. It's an RL circuit. Again, if you allow a current to flow through this, as you can see, the switch can be flipped on, and you will see that the current through the circuit grows, and it grows exponentially, and the growth of this current is given by I is equal to I naught, which is the maximum current, 1 minus e raised to minus RT by L. And the decay of current is given by a similar formula, except for the 1. You see, it's I is equal to I naught e raised to minus RT by L. And this ratio of the inductance to the resistance is called the time constant. So the time constant is the ratio of L to R in this. And it's actually the time taken for the current to grow to 63.2% of its maximum value, or to decay to 36.8% of its maximum value. So that's the time constant, and that's an LR circuit. So now we come to the final section of this chapter, where we're going to see how an inductance, a capacitance, and a resistance behaves when an alternating source is applied to it. So here we have an alternating generator connected to an inductor. Remember, an inductor is just a coil. For the time being, we are assuming that this coil has no resistance. So it's a pure inductor. And when you have this EMF applied to the inductor, there is going to be a current flowing. But look at the patterns of the voltage and the current. You see that the voltage and current do not rise and fall together. They do not hit their peak values together. In an inductor, remember that the voltage always is ahead of the current by 90 degrees or pi by 2. If you look at the voltage graph, the green one, you see the voltage is already at its maximum when the current is at 0. Do you see that? The voltage is at its maximum when the current is 0, which means the voltage is leading the current by pi by 2 radians or 90 degrees. And this inductor is going to oppose the flow of current. The opposition of flow of current by an inductor is called a reactance. Instead of a resistance, we use the word reactance. Now, specifically, this is called inductive reactance. It's represented by X sub L. That's inductive reactance, and it's given by omega times the value of the inductance, which means that the opposition depends on the frequency. So higher the frequency, bigger the reactance. So two things: the voltage leads the current by 90 degrees, and inductive reactance is dependent proportionally on the frequency. Higher the frequency, higher the reactance. On the other hand, when you look at a capacitor connected to an alternating source, both of these things are kind of opposite. Number one, the capacitive reactance X sub C is 1 by omega C, which means it's 1 by 2 pi Fc, which again means that as the frequency increases, the capacity of reactance decreases. That's the opposite behavior of what the inductance behave like. And also, look at these two graphs now. You see that the green one, which is the voltage here, the green one is the voltage, is right there as before. But now do you see that the red line, instead of going up, is now going down first? That means it's the voltage that's behind the current by 90 degrees, or voltage lags the current by pi by 2 or 90 degrees. I hope that makes sense. But if you apply the same alternating generator, alternating voltage to a resistance, we know that the resistance value is given by Ohm's law as V by I, and there is nothing to do with frequency there. So resistance is independent of the frequency, while reactance depends on the frequency. And also, you see that the red and the green, the voltage and the current graphs rise and fall in phase. So they are in phase. The voltage is neither lagging nor leading. They are together. They rise and fall together. To summarize, in an inductor, the voltage leads the current. In a capacitor, the voltage lags the current. And in a resistance, the voltage and current are in phase with each other. Come to a very important scenario where you have the three, the resistance, the inductor, and the capacitor, all three connected in series. This is called an LRC circuit. All three are connected in series, which means the current flowing through them will be the same, right? And all of these are connected to a source of alternating voltage. And remember, alternating voltage is given by V is equal to V naught sine omega t, which is 2 pi ft. Okay? Also remember that the voltage across the resistance is the product of current and resistance. The voltage across the inductance here is the product of current and reactance, and so too the voltage across the capacitance is the current multiplied by the capacitive reactance. Notice that the currents through all three are labeled I because the currents will be the same. All right. So that is an LRC circuit. And if you look at this, we have looked at this before. You see that the resistance, in the resistance, that's the current. The voltage and current are in phase. But in an inductance, the voltage is leading. As you can see, it's leading the current. While in a capacitance, the voltage is behind the current. So when you have these three different behaviors and it's together, what's happening to the resultant voltage? What about the resultant voltage? First of all, the magnitude of the resultant voltage is given by this formula. You got to take the square root of VR squared plus VL minus VC. And it's chiefly because the voltage across the inductance and the voltage across the capacitance are opposite. So that's why we take the difference between the two and then you add it to the square of the voltage across the resistance. But remember that voltages are the products of currents and either resistance or reactance. So square root of I squared is I, that's taken out. And then you have I multiplied by a quantity. If you take a look at this quantity, it's neither a resistance nor a reactance. It's a combination of a resistance and a reactance. A combination of a resistance and a reactance is called an impedance. It's called an impedance. It's represented by Z. So we write this as Z, where Z is the impedance. And what's the value of Z? Z is square root R squared plus XL minus XC whole squared. And here I was trying to show the diagram whereby you get that formula. See, the voltage across the inductor is positive, voltage across the capacitor is negative. So first you take the resultant of the two, you get that vector, and then you have the voltage across the resistance in phase with the current, and then you find the resultant of these two vectors, and that would be the resultant, which is V naught, which is what we have written. Okay, so this is going to be a very important question in any exam. So get used to it, get used to the calculations. All right. So in an LRC circuit, there is something called resonance that happens. And basically resonance happens when these two voltages become equal to each other. Okay, so one is positive, the other is negative, and if they become equal, then they surely cancel out. And when they cancel out, we have the impedance. Let me go back. The impedance is just going to be the resistance, because these two become equal, right? It cancels out, and square root of R squared is just R. So that means the impedance becomes minimum. Why minimum? Because you have made this quantity 0. So impedance at resonance, impedance becomes minimum. That means the current becomes maximum. So that's why when you look at this graph, you see that the current increases, but at resonance, for that particular frequency, the current is maximum, and then if you keep on increasing the frequency, it decreases. So this is called a resonance curve. Okay? And we can get the frequency at which resonance happens simply by understanding that resonance happens when the inductive reactance becomes equal to the capacitive reactance. So put them equal to each other, and then we get minimum impedance, which is the resistance. But also, let me slow this down, inductive reactance is omega L, omega times the inductor, and then capacitive reactance is 1 by omega C. So now if you bring this omega to the other side, because omega squared is 1 by LC, or omega is 1 by square root of L times C. But remember, omega is 2 pi times F. So you could have written 2 pi F here. So when you have F alone on the left side, you know 2 pi is gone to the denominator. So this is the formula using which you calculate the resonant frequency. Let me ask you something. Does the resonant frequency depend on the value of the resistance? No. There's no resistance in this formula. So the resonant frequency does not depend on the value of the resistance, but how big the current is at resonance depends on the resistance. That's why you have two graphs here, one for a smaller resistance, the other for a larger resistance. You see that the current becomes maximum at this frequency for both, but the maximum value of the current is much smaller here than for this one because the resistance is small. I hope that makes sense. So that's resonance in an LCR circuit. And then at resonance, this is like resonance in sound. You remember what we did with the resonance column. Energy, actually, it oscillates between magnetic field and electric field. I want to summarize this chapter and say, the inductor stores energy as a magnetic field. A capacitor stores energy as an electric field. Now, and the energy oscillates between the two. Imagine a simple pendulum. You pull it to one side, let it go. Before you let it go, all of the energy is potential energy. But as the pendulum bob swings down, the potential energy changes to kinetic because its speed is increasing. But when it goes to the other side, again it becomes potential. So you see that there is oscillation between potential energy, kinetic energy, potential energy, and again kinetic energy, and so on. In the same way, this is called an oscillator because here the energy is oscillating between magnetic energy of the inductor and electric energy of the capacitor. That's what these diagrams show. So look at this. Here all of the energy is electric between the plates of the capacitor. No energy across the inductor. But here you see that all of the energy is now magnetic and nothing here. Again, you see that the energy has become electric, but notice the direction. Now the electric field is opposite to what it was initially. And once again, it becomes a magnetic field. And again, the direction of the magnetic field is opposite. You see, that's called an electrical oscillator. Thank you for listening in. Thank you for watching this video. I know this is a tougher chapter because there are many concepts, but it's also a more important chapter. And I hope you have understood all the concepts in this magnificent chapter. But I'm so much in love with physics that this is one of the most interesting chapters practically. Thank you and good luck.